Today we're going to learn how to do the ideal gas law problems. With ideal gas law is written right here. You should have already watched how we derive the ideal gas law from the combined gas law. So it's P for pressure, V for volume, equals N for number of moles, R, which is the ideal gas law constant, and T. Now, the only trick to this is we know that T has to be in Kelvin. V, in this case, we can't use milliliters here, where it's going to have to be in liters. And number of moles, or N, is going to be in moles. So the only thing that we have to be wary of is the pressure units. Pressure can be a couple different things. There's a couple different versions of the R value, whether you're using kilopascals, atmospheres, or millimeters of mercury. I always just convert to atmospheres. If you convert to atmospheres, you're using the value 0.0821 liters atmospheres per moles K. Sometimes you'll see it as 0.08206. That's the same number, just to a different number of sig figs. We're not going to let that confuse us. So if I'm in atmospheres, this is the value I use. If I'm in kilopascals, this is the value I'll use. If I'm in millimeters of mercury, this is the value I'll use. The equivalency statement is 101.3 kilopascals equals 1 atmosphere, and that equals 760 millimeters of mercury. These are reference values, so these are considered to have unlimited significant figures. You do not use these conversion factors to determine the number of significant figures. So you can take any of these. If you need to change kilopascals to atmospheres, let's just say you have 73.9 kilopascals, and you want to change it to atmospheres. Well, in order to cancel kilopascals, you put it on the bottom, and the unit you want to go to goes on the top. The numbers stay with them. Atmospheres always stays with 1, and this conversion factor, 101.3, always stays with kilopascals in this conversion factor. So as long as you can convert between any of these units, as long as you're canceling out the 1 by putting it on the bottom and converting to the 1 that you put on the top. And I would get 0.730 atmospheres. Same thing, let's just 793 millimeters of mercury. Let's change it to kilopascals. I put millimeters of mercury down here to cancel. Remember the pattern. Whatever's in your given always goes in the next conversion factor on the bottom. And then I'm going to change it to kilopascals. Millimeters of mercury stays with 760. 101.3 stays with kilopascals. So 793 times 101.3 divided by 760 will give me an answer of 106 kilopascals. Remember, we go to the given in order to find the number of significant figures. So this is just another conversion factor to convert between units. Let's do our problems. A sample of carbon dioxide gas with a mass of 100 grams is placed in a 500 milliliter container at 350 K. What is the pressure exerted by the gas in kilopascals? Now, I told you I typically change from kilopascals to atmospheres when I'm doing these problems, but I'm going to do them for you now because you might decide you just want to use the different versions of R, which is fine too. So we have 100 grams, which is a mass. We know we can convert that to moles. So if our mass is 100 grams, we use the periodic table of the elements to change grams to moles. So in 1 mole, you add up two oxygens and 1 carbon, and you get 44.01. And that's going to give us the number of moles. You can convert inside the problem, but I usually just convert before I add in. I'm going to carry around an extra significant figure here. This problem really only has one significant figure. And next we have a volume of 500 milliliters. But you see in these, all of the units of volume are in liters. So we're just going to go ahead and change milliliters to liters. We know that there's 1,000 milliliters in 1 liter. Or you can think of just moving the decimal point over 3 spots too. And then my temperature is already in the units we want, which is K. If it was in Celsius, we'd have to change it to K. We're solving for pressure, and we want it in kilopascals. So I'm going to go up here and I'm going to pick the value for R that has kilopascals in it. So R is going to be 8.314 liters, kilopascals on the top, moles, and K on the bottom. That tells you what units you're supposed to be using in your problem. Let's go over here and rearrange our ideal gas law to solve for pressure. So it's PV equals nRT. I'm going to get P by itself by dividing both sides by volume. That allows me to cancel this out, and my formula becomes P equals nRT over V. So 2.272 moles, 8.314 liters, kilopascals, moles, K, times 350 K. All of that is over a volume of 0.500 liters. Now we're going to check that the units cancel out, because if your units do not cancel out correctly, you've probably made a mistake. So moles on the top cancels the moles here, K cancels with K here, liters cancels with liters here, and this is in kilopascals. Now I get an answer in my calculator, 13,222 kilopascals. And we'll just, if we wanted to round it to 1, it would be 10,000. So let's just stick with that. Next one, sample of N2 gas is placed in a 250 milliliter flask. Again, we'll change this straight to liters by dividing by 1,000, or moving the decimal point over 3 spots, 250 liters. Temperature of 298 K and a pressure of 1 atmosphere. So we're using atmospheres, so our volume, our R value will be 0.0821 liters atmospheres per moles K. And we're going to solve for N, because we know we can go back and forth from grams to moles very easily. So let's go over here and rearrange our ideal gas law equation, PV equals nRT. In order to get N by itself, we divide by R and T. My formula becomes N equals PV over RT. So 1 atmosphere times 0.250 liters over 0.0821 liters atmospheres per moles K times 298K. Let's check our units. Atmospheres, atmospheres, liters, liters, K. We're left with moles on the bottom of the bottom, which brings it up top. So this answer is going to give us the number of moles. 0.01022 moles of N2. And then we can change this to grams easily with the periodic table of the elements. 1 mole, careful, it's N2, so it's 28.01 grams, not 28.02 grams, not 14.01. .2863 blah 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 grams of N2, and we'll answer to 1 sig figs would be 0.3 grams. Last one, a sample of O2 gas with a mass of 50 grams. Let's change this right from grams to moles. It's O2 gas, so it's 32.00 grams per mole. And this will give us the number of moles for our ideal gas law problems. Volume is a 300-liter container. Let's just move the decimal point over 3 spots right away. So it's 3.3 liters. Under pressure of 770 millimeters of mercury, and we're looking for the temperature. The R value, let's go look up here and find the R value for 62.4 millimeters of mercury per mole. It's going to be liters, millimeters mercury, over moles K. Let's talk about this millimeters of mercury real quick. A barometer is a piece of equipment that looks like this. I don't have a barometer anymore because they frown on us having mercury in the classroom. So it's a contraption that looks like this. There's a pool of mercury down here, and the atmosphere pushes down on us, also pushes down on this open pool of mercury here. And what happens is it forces it up this column here. So the mercury will rise up this column. The greater the pressure, the higher it will rise in the column. Then you take a ruler out and actually measure the height of the column and how many millimeters up you have. That's how many millimeters of mercury. So that's where the unit mmHg comes from. That's why I hope that millimeters of mercury kind of fades out, because it's an antiquated unit due to the fact that not very many people have mercury barometers anymore because of the dangers of mercury. So PV equals nRT. We're going to solve for T. We'll divide by N and R to solve for T. These cancel, so T is equal to PV over NR. Now let's plug in P, 770, V, 0.3 liters, N, 1.5625 moles, R, 62.4 millimeters of mercury over moles K. Millimeters of mercury cancel. If you use the wrong value of R, your units aren't going to cancel, so that's going to be your dead giveaway. Temperature is going to be very cold, 2.369 K. So this is a couple examples of the ideal gas law. Again, if you want to simply straight off the bat convert to atmospheres, it's good practice converting, and then you will be able to use just one value of R. But that's a judgment call on your part. Just remember that your units of R are the cornerstone here. It's always, let's solve for R. PV equals nRT. So we're going to solve for R by dividing both sides by N and T. And R is going to be PV over NT. The units of P are the ones that can vary. They can be atmospheres, millimeters of mercury. Volume has to be in liters. Number of N has to be in moles, that's amount, and temperature has to be in K. So our three units of pressure will determine which value to use. But the other units have to remain constant. And you can convert between these R values also using the conversion factors that I wrote up above. And there's your ideal gas law.